All right, so I'm making this video kind of with no power. This is battery power. Hopefully this works. My power's been off for about an hour, so hopefully I'll be able to upload this tonight. Okay, so today I'm talking about Euler's method, and this will get you through worksheet 35. So first of all, for Euler's method, okay, Guy is a German dude, so his name is Euler, not anything else that the students like to say instead of Euler. It's only Euler. Okay. All right, so you would start off with some point, like I'm just going to call it AB. I have a real hard time making vertical lines. There we go. I mean, yeah. So you have a point A, B is your starting point, and you have a slope field, which we were talking about in the last video. So a slope field is a slope field, which is going to tell you essentially y prime of your function. And what you do is you play this kind of like connect the dots. You make these little hairs of the slope field and you follow the curve along, and that's your path. Now, in theory, if you could make the steps really, really small, then you would have a perfect answer. But of course that's not true because you can't make the steps perfectly small. We also assume we're going in the direction as x increases. You could run this algorithm backwards to follow the curve back from where it came from, but we're just going to assume x is going to increase for us. Okay? So let me give you an example. Let me give a specific example. And since you have internet and I don't, you guys can go use those websites that I talked about in the last video, and you can plug this in and see what it does if you like. Okay, but I'm going to just pick the point 1, 1 as my starting point, and my slope field is going to be x minus y. And I also need a delta x, and I'm going to let it be 0.1. Let me show you what we do for Euler's method. So we take the starting point, whatever it is. I'm going to move it a little bit here. There we go. And then I'm going to calculate what the slope field will be. In this case, it's 0. I'm going to make a little line to say that that's 0. I'm going to go a little delta x over to the next nearest step. So if this is 1, 1, this is 1.1, and it's actually still 1 because the slope was 0. And then it's going to change a little bit. So my new slope is going to be x minus y. So the new slope is going to be 0.1. So it's going to slightly tip up, and it's going to keep going up, up, up like that. Okay, so let's be a little more methodical about how we would do this. Talk about what we're doing. So making a step. So what do? You're going to start at a certain x and y. So start at x equals 1, y equals 1. And then you're going to step, the x's are just going to march along like this as far as your heart's content will take you. And then you have to create the y based on everything else you know. So let's start here and do a couple steps and see how this works out. Okay, just like so. All right, so we already said that when we make our first step, we're going to still have y equal to 1, and that's not going to be true for the next step. So let's figure out how this works. I'm going to use the plain old y minus y1 equals mx minus x1 that we know from high school. This is going to be whatever your previous step is. It's going to be x1, y1, and then it's going to be x2, y2, but it's whatever your previous step is in this table here. And then y is your new y, and m comes from f. But which x and y do you use? Well, of course, you know the one you use. You're using the one you already know. Okay, So what we want to do is we want to plug all this stuff in. X we know. We know this. It's going to be, this whole thing here is just going to be your delta x, so you don't have to calculate it. This step size is constant for this method. And then y1 we know is their prior y value. Okay, and so we can just make this look a lot cleaner. I'm just going to rearrange this and I'm going to rewrite this so you know what it looks like. Y new is equal to y old plus delta x times f of this x and y. I'm sorry, I'm putting the formula in there. And these are the previous. So let me just write it as x old comma y old. So you use all the things from the previous step to get you to the new step. So let's go ahead and do step 2 together. Or you could pause the video, do it, and come back. So the y is going to be equal to the old y plus 0.1 times, okay, what is x minus y? It's just 0.1. So y in this case is 1.01. Okay, and you can keep going with that, but it's just kind of annoying, isn't it? So let's go ahead and figure out what it's going to look like if we do this in Python, which I encourage you to do. I encourage you to do 2 steps by hand and then write it in Python and double check the first 2 steps that you did by hand. So I'm going to tell you what your code should look like, and then we're going to type it in. So let me just pause for a second while I type this for you. Okay. So I've rearranged the screen a little bit to make things cleaner. I'm just going to comment on how this code works. I'm going to do this on my computer rather than at repl.it because of course I don't have internet. But if you Google repl.it and Python 3, you should be able to do this online if you don't already have Python on your computer. So you don't have to install it just for this one exercise. Don't worry about that. You can just use a freebie copy. Well, it's all free anyway. All right, so first of all, this is just a variable, and it's the step size for dx. So that's a size that we're stepping over in x. This is just, I'm starting our initial point, which was x is 1, y is 1, but these are arrays that are going to grow. So I'm going to push these arrays out for all the values that we're calculating. As if you notice, the x just keeps, you keep adding dx. The -1 is Python trick. It just means go to the end of your array and use the last value of the array. So I don't have to worry about how long my array is. It just means take the last item in x and add, in this case, 0.1 to it, and then pop that on, make that the new last value in the x array. The y array is going to use this magic lambda function. Lambda is really, really cool because you just put, you know, a pair, 1, 2, 3, however many inputs you want. Give them each a different name, separate them off by commas, and then after the colon, this is the expression you want that function to return. So it's a very, very easy way of making functions on the fly. And so that's what this is doing. This f is literally the f that we had in the exercise, and this is the x input, and this is the y input. And I'm always taking the most recent value of x and y, shoving it into x, multiplying by dx, and then adding that to the old y. Okay, so I can just say print xy, and that's the lazy way to do it because it comes out a mess on the screen, and I'll show you. Or if I want it to come out in columns, I could do this to it. So let me just pause for a second while I put that in Python for you. Okay, so I've typed all that in, and now I'll show you what a big mess this makes on the screen if I just spit out x and y like that. So, and by the way, 10 is just a number I picked. It could be anything, right? So for I in range 10, I'm not even really using I, but now I am. I'm just going to say print the X and the Y separately on a line. Hey, I just got power back, maybe. Who knows? So I have two columns of answers, and there I go. So let me see. I agree with myself. It was 1.01. I'm happy with that. That's good enough. I'm convinced that the computer is doing what I wanted it to do because I did the first 2 steps by hand and verified that the computer answer was the same. So I'm just going to assume that all those are correct. All right, I have a couple other comments. One is if you need to use math. So we don't know even what sine of 0 is. We don't know what pi is. But if you say from math import star, there's more than one way to use import. My preferred way for this course is to just import math like that, and then everything just works. Like sine of pi over 4, you just get the answer back out. So you've just imported sine, cosine, tangent. I think you may have already had square root. But anyway, you have a whole bunch of functions now that you thought you had and you thought you should have. Let's see, log of 6. Log of e. There we go. So we got e and we have log of e. So log means natural log. So you have your functions that you want. Be careful that 8 to the power of 2 is not written this way. To make 8 to the power of 2, any kind of exponent, you put 2 stars. And you may be like, oh my gosh, how does 8 squared equal 10? Well, this is special for you guys because you're Calc 2 and you can handle this kind of thing. If you know about binary, listen to the rest of this little blurb. This is the number 8 in binary. Oh, this is binary. This is base 10. And the number 2 in binary is just like so. And then what we're going to do is we're going to XOR them together. That means exclusive OR. It means one of these is true, but not both of them. And that number is 10 in binary. So if you ask 8 XOR 2, it's going to be 10. It's going to actually add them in this case, but not always. It's not always going to add them. But if you flip any XOR, it's got to be the same right and left. So if 8 squared is 10, then 2 squared is 2 to the 8 is 10. Anyway, very silly. But anyway, that's just a little demo. So if you want to square, just make sure you do that. If you're a little hesitant, then just multiply 8 by itself. You know, in your formula, if you have x squared, you can just write x star x, and then you don't have to worry about it. So let's see. Something that we often like to do when we're talking about Euler's method is we like to ask students if we're getting an over or an underestimation. So this is based on curvature. If you have positive or negative curvature, that is the trick. Okay, so let's just look at this simple example. If you have a curve, any kind of curve that, for example, is always concave up, or a family of curves that are always concave up, and you're trying to do Euler's method, you will consistently underestimate because you're going to take a step here and you're not going to, your slope isn't going to change fast enough. Even if you're going down, this is true, you're still going to shoot under the curve, right? So if you're concave up, you're going to wind up under the curve. So concave up causes you to be under the curve. However, that doesn't necessarily mean the absolute value is too low. Just keep in mind whether you're talking about, you know, absolute value or not. But strictly speaking, as long as you're concave up, you're going to be under the curve. And then as long as you're concave up like this, let's say you have a curve, some kind of a curve that's concave up and you're trying to follow it with Euler, you're going to consistently be above the curve. So if a concave, I think I said that backwards, but what I wrote, not what I said. Concave down causes you to be over the curve. Okay, so there you go. That's what you need to know. And there's a little bit of a silly question for you on the worksheet. So just warning, just answer the question correctly and you won't get stuck. All right. Sometimes there's trick questions on worksheets. Okay, I think that's all you need to know, and that's video 35. Just got a couple more left.